So once again, very good morning to you all. So today we are going to start memory systems. That is, so far we have been talking about the CPU, data path and control side of the story of our computer architecture. So we first started with some assembly, ISA and assembly instructions, ARM architecture and all that. Then we went into the organization, the microarchitecture using the MIPS ISA. Now we'll be talking about the other side of the story, the memory. And so the memory these days plays as big as a role as the CPU itself. So there are a lot of things to talk about in on the memory systems. So, but before we get into the technical details, let's talk a little bit about some history of memory systems, where how all this memory idea of memory came into being. So, if you go all the way back to say 1940s, long time back, this was way before transistors were a thing. So those very early computing machines, you probably have heard about things like ENIAC, Mark I from Harvard. Have you guys heard these names? Ancient computer systems. Yeah. What other old ancient computer systems have you guys heard about? Famous old computer systems. Any names come to mind? ABC computers. There are a lot. So the ENIAC and Harvard Mark I, all those things are from the United States, and there are a lot of other developments in Cambridge, United Kingdom at the same time, around the same time as well. So you probably heard about names like Charles Babbage, Icon and all that, right? So those are the names that we use in our servers at the department. So very famous computer engineers or scientists, mathematicians who built these ancient machines. Anyway, so these very first computing machines, so to speak, things like ENIAC, which was developed by University of Pennsylvania, and Mark I developed at Harvard University, which is actually the name was, the official name was ASCC, but it was affectionately known as Harvard Mark I. Right, so these computers, which were built in around 1940s, they didn't really have a concept of memory or software as we know software today, right? So these machines, these are machines, we are talking about machines which filled massive rooms, big machines which were made using vacuum tubes and all kinds of electrical, old ancient electrical circuitry, big wiring, big chunks of electrical machinery. So there were no real concept of software as we know software today, and there were no real concept of memory also, right? So so these machines were developed for computation, so rather calculations, computations or computers. At that time, the term computing or computers were used for people who did calculations, mathematical calculations for certain tasks, like routinely did mathematical calculation. For example, if you were to go to 1940s back in time and ask for a computer, you would probably be pointed to a person who is as a job doing some mathematical computation, right? So computers are like that back in those days. So these machines were built to sort of automate, quickly do these calculations, mainly for war-related matters. So 1940s was that time where World War II was on about, and most of these, not most, all of these ancient computers, the first computers were developed to support certain war efforts, do computations for artillery planning, and even say things like the nuclear weapons that were first used in the World War II. Those things, for those things, these computers are developed to do the necessary calculation for those things. Unfortunately, like most great technologies, computers also came out of such a dark history, if you will, right? So anyway, so the idea is there were no real concept of software and memory back at that time when computers were first being built. Then in around the same time, in 1936, you probably have heard about this person, Alan Turing, a great mathematician, brilliant guy from United Kingdom. So yeah, so I hope you have seen the movie about him, which was recently made. Yeah, Enigma Machine Inventor. The movie which this guy Benedict Cumberbatch acted, played this role, Alan Turing. What was the movie? The name doesn't come to me now. Imitation Game. Yeah, exactly. So that was about his Alan Turing's involvement in World War II, where he broke certain encryption cryptographic code. He actually built a machine to do that. So way before that happened, around in 1936, he was the first person to come up with this idea of a stored program computer, right? Mind you, this is not he didn't design an electrical device or anything. It's a hypothetical machine. He devised a hypothetical machine. He designed a hypothetical machine, um, like a finite state machine, if you will, a more complex version of a finite state machine, which can actually represent something like a stored program computer. So the first notion of memory and a program being put into the memory, data being used and read and written to and from the memory, was first conceived by this guy, Alan Turing. So, right. So this hypothetical machine we now refer to it as the universal Turing machine. Some of you may have some familiarity with it, but yeah. So that was the machine, or the first instance where the stored program computer was proposed, so talked about, but it didn't come into real being for a long time. So that was around in 1936, right? So a long time before World War II also. So then in 1940s, these machines like ENIAC and Harvard Mark I were being developed in United States for to support this war effort by United States Army. So machines like ENIAC, they were commissioned by Army, like they were paid for and requested by the Army. And around that time, there was this person, John von Neumann. Have you heard about that name? Anyone heard of John von Neumann? And maybe we mentioned his name at the beginning of our course also. Von Neumann architecture, von Neumann machine, right? So, yeah. So, von Neumann was actually he's regarded as the last of the brilliant mathematicians that humans ever had. So we're talking about people like Galileo Galilei and Isaac Newton and all that, right? So this John von Neumann was known as the he is widely regarded as the last of these great mathematicians. He was like a brilliant fellow, arguably even more brilliant than Isaac, who's this fellow, Albert Einstein. But yeah, that's just the thing. But yeah, someone who was a prodigy. For example, by the age of he was a Hungarian. He was Hungarian by birth. Later moved into United States. So in Hungary, around the age of 8, this guy was solving um, uh, integration and calculus problems, right? Around the age of 8. Like you and I were probably drawing stick figures by that time. So yeah, he was like a prodigy, a brilliant fellow who contributed to all kinds of different fields, computers being one of them. So he set certain concepts at that time, which later led into the computer technology that we have today. So there's some argument who is the father of computing, and some say Alan Turing, some say von Neumann, but both of them made big contributions. So this fellow John von Neumann, he was acquainted with Alan Turing and his work, his hypothesis on this stored program computer, the Turing machine. So based on those ideas, von Neumann got involved in this other computer called EDVAC, which was developed in the late 1980s, around 1940s, 1948 or something, which was also commissioned by the United States Army to build a computer to again support certain war efforts. Right, so if I remember correctly, the first test programs that were run on EDVAC were something to do with the detonation of the hydrogen bomb, which was later dropped on Japan. So yeah, dark history. But anyway, so EDVAC was being developed in University of Pennsylvania by a group of engineers. So John von Neumann got involved in that project in a sort of a consultant role. Then he, based on Alan Turing's proposals, he put certain ideas into the design where this stored program concept was actually memory and stored program concept was actually implemented. So earlier machines like ENIAC and Harvard Mark I and all that, they didn't have a stored program concept. So how was it programmed? People, engineers had to rewire the entire machine for a given algorithm, right? So if you want the machine to solve some algorithm, right, do some computations based on an algorithm, the engineers had to rewire the entire machine, right? So imagine rewiring an entire room, big room. So you had to spend days and weeks programming those old computers. So in this EDVAC, they introduced this concept where you had a memory, electrically supported memory, and the program can be put in the memory, right? Not in the wiring. So in that early implementation of EDVAC, the memory size was it could support 1044-bit words. A few months later, after it was completed, it was upgraded to 1024 44-bit words, because us computer guys, we love binary arithmetic, binary algebra. So yeah, so 1024 44-bit words when it was commissioned, when it was deployed. So that machine was the first to have this notion of stored program computer. The engineers of EDVAC, they sort of dispute that John von Neumann John von Neumann's ideas were the major ideas behind the design of EDVAC. Because one of the key points that John von Neumann stressed, they tried to include in there, was having the program and the data itself both in the same memory and accessing those program and data using the same access pathways, same connection pathways, right? Having data as well as program in the same place, same memory, and accessing them through the same connections. That was John Neumann's key concept, key characteristic concept. So that concept was not actually incorporated in EDVAC by its engineers. Because of that, they sort of dispute John von Neumann's involvement. But a little later, about a year later, this idea of having everything in the same place, all data and program both in the same place and accessing them through the same connections, which now we know as the von Neumann architecture. We refer to that as the von Neumann architecture. That was used by the Cambridge University engineers and scientists to build this machine called EDSAC, again in the World War II period, for war effort. And this EDSAC was the first machine built or implemented using the von Neumann architecture. So that machine, it had 512 18-bit words, so a smaller memory. On the contrary, or in comparison to that, the Harvard architecture, we know what Harvard architecture is today, and that is where we use separate storages for instructions and memory. Like we discussed in our MIPS data paths, we have separate instruction memory and separate data memory, and we have separate connections going to them, right? So that is the key characteristic of the Harvard architecture. So modern day computers, right, the computers that we have today really use a mix of both types of architectures, von Neumann architecture and Harvard. Features from both are used in the modern day. And we also have several levels of memory connected as a hierarchy, right? So we have, say, main memory and caches, and level 1 caches and level 2 caches and all that, right? So several levels of memory, which is organized in a hierarchy. That's what we have today in reality, but the history is like that. In the earlier days when computers were developed, there was no concept called memory or software to store in a memory. Even data were input as punch cards, data were output as punch cards. So yeah, so that is a bit of a history to sort of get the big picture where we came to what we have today. It's always good to know the history, right? Okay. So with all those things in mind, let's talk a little bit about different memory types that we have today in common use. So these are some of the commonly used memory technologies, right? SRAM. You probably have heard about it. SRAM, DRAM, flash, magnetic disk, magnetic tape, right? So different memory technologies that we have in use today. So let's talk a little bit about some characteristics of them. Let's try to compare them. So SRAM is mainly built using flip-flop. SRAM is basically static RAM, and it's built using flip-flop. So it's a volatile type of memory, meaning if you lose power, after a little bit of time, you're going to lose the content of the memory. So it's volatile. Built using flip-flops, and access time is less than 1 nanoseconds most of the time. So these are approximate values, not absolute values. So in most SRAM based memory implementation, access time is around 1 nanosecond. Access time is the time between you sending a request and getting the result, right? So you can assume the memory getting the request and outputting the requested data. That is the access time. Access time is less than 1 nanosecond for SRAM device. They can operate at more than a gigahertz clock frequency. And cycle time is also less than 1 nanosecond. Cycle time in this context is um, the minimum time between two consecutive memory accesses. That is the minimum time between a start of a memory access and the start of the next memory access. So how long does it take for the memory to be ready to serve the next memory access? And their access time and cycle time are mostly similar for SRAM. And the capacity, we know kilobytes and megabytes, that in that range we have SRAM implementations, because the cost is massively high. Cost per gigabyte, just to compare, cost per gigabyte of SRAM memory is around $2,000. So that's a massive amount of money. And that is why it costs a lot. It's really fast. So we can only use small amounts of it. We can only afford to use small amounts of it. So things like cache memories are built using SRAM. And those are really fast memories, right? Really, really fast memories. And the capacity is usually around several kilobytes or several megabytes, right? Not more than that. You don't go into the gigabyte range with SRAM because of this cost. Then DRAM is the most common technology used for main memory, right? So in the most in our computers that we use, we have DRAM memory, dynamic RAM, and the technology behind those DRAM implementations are transistors plus capacitors. So a cell of DRAM uses a transistor as well as a capacitor. So you need to keep refreshing these DRAM memories in order to hold their values. So not having power is just enough, but you need to keep refreshing the memory as well. Otherwise, you lose the content of these memory cells. So the capacitive charge. So the performance-wise, access time is roughly around 25 nanoseconds. So that's compared to SRAM, quite a big access time. And the cycle time is about double the access time. The reason for this is this having to refresh the memory periodically or regularly. You need to refresh the memory cells in order to retain their values. So you can't say when you read the content of a memory cell, you are prone to lose the content. The read is called a destructive read. When you read the content of a DRAM memory cell, the charge is actually lost when you do the reading. Then you need to sort of rewrite, if you want to imagine, rewrite the same data onto the same cell again. Or in other words, to refresh the data again. So you need to, your cycle time is actually double the access time of a single read. So you need to wait a longer time in order to be ready to serve the next memory access, right? So cycle time is quite long compared to access time for DRAM. And capacities, we know that we have several gigabytes of RAM in our computers today. 16 GB, 8 GB and so on, even more than that based on the power of the computer or the requirement. Cost per GB is around $10. 1 gigabyte of RAM, around $10 or so. It's a rough number. So that was DRAM, and then we have flash memory. Flash memory is, so DRAM, while SRAM and DRAM are volatile memories, flash and disk are non-volatile, meaning you can retain the data without power. So Flash memory is now being used as the standard secondary storage, right? This SSD, solid state devices, solid state memories are built using flash technology, or these portable storage devices. A lot of them are flash technology based. So the technology behind them is NAND MOSFET. The effect is like a NAND gate implemented using a MOSFET. MOSFET having two gates inside it, acting as an AND. So that's the technology behind it. You can go and search about the technologies if you want to know more. We don't have a lot of time to discuss them in detail. The access time for flash is around 70 nanoseconds, and cycle time also 70 nanoseconds. So it's closer to DRAM, right? It's only a little bit slower than DRAM, but the write and read cycles, there's a number of cycles that a flash device can support, a cell of flash can support, to guarantee that the data is not corrupted or lost after reading and writing. So after you use a flash device a number of time alone, it's a large number of times, several thousands, but once you pass that number, you tend to lose some memory cells. The integrity of some memory cells will start to go down. So the actual capacity starts to go down. So the capacity is again just like DRAM memory in gigabytes range. Cost is a lot less actually, around say less than $1 per gigabyte of this, right? So you can have larger devices implemented using flash technology, larger memories. So secondary memories, it's a good option. Then disk, we know, right? Magnetic disk implemented using magnetic technology. Access time is way high compared to the previous numbers, right? Previous numbers are in the nanoseconds, so even smaller range. Magnetic disk, you know, it's a mechanical device, right? Access time is 5 to 10 milliseconds roughly. Cycle time is somewhat similar. These are average numbers, but depending on where your data is located on the disk, the time that you spend to reach it, it actually varies, right? So you know how a disk operates. Spinning, you need to bring it up to speed and then move the head to the correct location and all that, right? So mechanical device. And the capacity is actually massive, several terabytes order. And the cost is really small, right? A lot less than $1, a fraction of $1 per gigabyte. So it used to be the main secondary storage technology choice, but these days flash is fast replacing disk as the secondary storage choice. Disk and other magnetic devices are very commonly used as tertiary storages, backup data backup, because they can retain the data for a long time and the cost is really low. And backing up you don't do all the time, you only do it periodically. So the time, the slowness of the device doesn't actually matter a lot for that, but the capacity and the cost helps, because you can have large amounts of data backed up. And so these are different memory technologies that we have, right? So with those numbers in our heads, can you spot a problem here? Now, main memory, right? So what we refer as the memory is, we say it takes around 50 nanoseconds to between the starts of two consecutive memory accesses. That is what the memory can support, 50 nanoseconds, right? So CPU cycle time usually is less than 1 nanosecond. 1 nanosecond corresponds to 1 gigahertz clock frequency. And we know that we have computers faster than 1 gigahertz clock frequency. So yeah, so our clock cycle is, CPU clock cycle is less than 1 nanosecond, while the memory is taking 50 nanoseconds on average between two memory accesses, between the starts of two memory accesses. So how can this work? There's something is not right. Yeah. So we say that in our pipeline, when we discuss the MIPS pipeline data path, the MEM stage, memory access stage, needs to finish in one clock cycle, right? One CPU clock cycle, like every other stage in the pipeline. So how can we do that? One clock cycle is 1 nanoseconds, and 50 nanoseconds is way bigger than that. So how can we get this done? Some trick has to be done to get this right. So otherwise, the memory stage in the pipeline is going to take a long time, long time compared to the other stages, and it's not going to, the pipeline is not going to perform as we thought it would, right? So that is where the concept of memory hierarchy comes into the picture, right? So that is where the things like caching comes into the picture. So the idea behind this memory hierarchy is to trick the CPU into thinking that the actual memory we are having is fast as well as large. We know that if you go back to the previous slide, we would like to have really fast access times like in SRAM, like what we have here, and the capacities like in disks, right? Larger capacities, also fast access times, right? These are two ideals, but they are not in the same technology. So the idea of a memory hierarchy is to trick the CPU into thinking that the memory is really fast as well as really large. So how you do that is implement in the memory as a hierarchy. So you have your SRAM based cache devices closer to the CPU, like physically closer to the CPU, and CPU directly access the SRAM. CPU thinks that SRAM is the actual memory. The cache is the actual memory, right? So all CPU sees is that CPU can only access that. CPU cannot access DRAM and disk in this scenario, right? In the hierarchy that we are showing here. So the CPU thinks and it experiences the fastness or the speed of SRAM. And from the way we will be designing the hierarchy, CPU will feel that you have the space of the DRAM as well as the disk even, right? At the speed of this SRAM device. So that is the idea. Trick the CPU into thinking that the entire memory is as fast as SRAM and as big as the lowest level in the hierarchy. So for now, we will be restricting ourselves to the two devices in the hierarchy at the highest place, SRAM, and the next place, DRAM, main memory and cache memory. So we will be restricting ourselves to these two levels in the hierarchy. We will look at the disk later. So just to refresh, the devices up the hierarchy are smaller and faster. Devices down the hierarchy become larger but slow. Right? So, right. The CPU only sees the top level and only can access the top level. See, so whenever the CPU wants to write to a memory location or read from a memory location, it accesses the SRAM device. But it thinks that it has a bigger memory like the actual memory you have in the system, the DRAM memory, right? So CPU imagines that you have this many spaces or slots in the memory, but it accesses the SRAM. So in order for our hierarchy to work, what we can do is each upper level contains a subset of data from the lower level. For example, SRAM device can contain a subset of data available in the DRAM device, right? So SRAM device is a few megabytes size. DRAM device is several gigabytes size. So a fraction of the data available in the DRAM can be stored in the SRAM. A fraction of the data available in the disk can be stored in the DRAM at a given time, right? So at any given time, each upper level in our hierarchy, it will contain only a subset of data from its lower level, right? Okay. So now we have a little problem. What if the CPU asks for something and that something is not available in the upper level or the top level memory device? So CPU asks for a memory location to read from a memory location, but it is not available in this SRAM device, the subset of data in this SRAM device from the DRAM memory. That subset doesn't include the data that CPU wants. What do we do in this situation, right? So to get this idea, so we will be talking about a lot of concepts and ideas behind memory hierarchy in the coming two or three slides. So to understand that better, let's take an example of a music library, right? So a lot of us listen to music, and let's say we use what do we use to listen to music most commonly? Say we keep some music that we like in our mobile phones, right? So mobile phones can these days hold a lot of songs, music files, and yeah, Jamit, you're right. Need to copy from lower level. Yeah. So let's get back to this music library analogy. So when we want to listen to music, we bring up our phone and find a song from there and listen to it, right? So that is like a subset of songs of that we might like to listen, but we would probably have a bigger collection of music in our computers, which we don't always take with us, right? We don't have the computer in our pocket. Instead, we have the phone. So we like to listen to music on the phone, but our main collection is in the computer, in our computer's hard disk. Okay, so somehow we bought the music or downloaded from some other means, and we have our main music collection in the computer, a subset of that in the mobile phone, and we plug our headset into the mobile phone and listen to the music when we want to listen to music. Then what happens when we want to listen to a particular song, but it is not in our phone right now? We need to listen to a song, some song, but that song is not in the phone right now, but it's in the computer's hard disk. So what we do is we need to go to the hard computer, go to our computer and copy that piece of music into our phone. So we'll listen on the phone, right? So that sort of a scenario is very similar to what we will be using in the memory hierarchy. And what happens if that song is not available in the computer as well? We can assume that all songs are available on the internet, right? Massive storage, and we can go to the internet and download the song from there, or buy the song from there and download onto our computer. That is like the hard disk in the memory subsystem, and then copy from the computer into our phone so we can listen it on the go, right, while we are moving. So in that example, the phone is like the SRAM device here, the top level device, which we always listen to music on. Computer is like the DRAM device here, the main memory, where we maintain our major collection, the main collection of data or of songs. And disk is like the biggest available. All the data are in the disk, we can assume, right? So all programs that are currently running and not running and data and everything are in the disk. So right. So keep that example in mind. We'll be using that in the coming concepts as well. Okay. Now, yeah. So like Chamit said, we need to copy from. If some data is not available in the cache or the SRAM device, we need to copy from the DRAM device into the SRAM device in order to serve the computer, right? So let's get some memory related terminology into the picture because we need to use these terms to talk about these different concepts, right? So if what the CPU wants in the SRAM, or rather if what the CPU wants is available in the SRAM, we have a hit in the SRAM, right? We have hit in the top level device. If what the CPU wants to find is available in the SRAM itself. So that is similar to you wanting to listen to a particular song and that song is already available in your phone, right? So you have a hit, you can just listen to it, right? And the other scenario, that data is not available in the SRAM device, we say it's a miss. We say that the access is a miss. We can't find that data in the SRAM here. That is similar to you wanting to listen to a song and that song is not available in your phone. So you will have to go and get it from your computer. So yeah, so an access can have two kinds of results. It can be a hit, it can be a miss, right? So hit is the data is available at that level. Miss is data is not available at that level, right? So then these two terms, hit rate and miss rate, they refer to how often you encounter these hits and misses, right? So if you simply saying, if you make 100 accesses to the SRAM, how many of them were served from the SRAM itself, or how many of those were hits in the SRAM? So if you had say 90 hits and 10 were misses, your hit rate is 90% or 0.9, right? So a ratio, hit ratio or hit rate, we commonly use the term hit rate. Miss rate is the opposite of that. What is the rate of misses? If we made 100 accesses to the SRAM and 10 of them were misses, then miss rate is either 10% or 0.1, right? So hits and misses, hit rate and miss rate, then hit latency and miss penalty. Hit latency is how long it takes for the device, memory device, to determine that the access was a hit or not, right? Meaning how long does it take to find the data in this SRAM device or whatever the level in, if you are referring to the memory, how long does it take for the memory to find the requested data? How long does it take the SRAM to find the requested data? That is the hit latency. So it takes that much time to decide whether the data is available here or not, right? So that time is referred to as the hit latency. Then miss penalty. If you determine that a requested data is a miss here, the requested data is not in the SRAM, then what you need to do is go to the next level in the memory hierarchy and fetch that data, right? Copy it from the DRAM into the SRAM. So the time it takes to go to the DRAM, find the data, bring it up here into the SRAM and put it in the appropriate place, that time is called the miss penalty, right? That is, if the access was a miss, what is the extra time you had to spend in order to serve this memory request to the CPU? If it was a hit, you only had to find here, it will take that amount of time. and you can give the data to the CPU. If it was a miss, it will still take that amount of time to know that it was a miss, but it will also take the additional amount of time to go and find the missing data and bring it up here, right? So that is the term miss penalty. Any questions about this terminology? Right. Okay. Now, with those in mind, how does this new concept of hits and misses and miss penalty affect the CPU performance? If you have a hit in the top level of the memory hierarchy, brilliant. You can serve the request, you can give the requested data to the CPU, and that is fine, right? So we know that SRAM devices, the access time is less than 1 nanoseconds. So you can determine the access was a hit or a miss before, way before that. So hit latency is part of that time, and then you can provide the data to the CPU under 1 nanosecond, right? Usually under 1 nanosecond. So you can fairly be certain that that access can be done within one clock cycle of the CPU, right? You don't have to stop the CPU. But if that access was a miss for some reason, if the data is not available in SRAM, we have to go to the DRAM and bring that back. And we know that DRAM is quite slow compared to SRAM, right? Can go up to 100 times slower, around 100 times slower than SRAM. So we'll have to stall the CPU. We'll have to tell the CPU to wait. I don't have the data here. I need to go to the DRAM and fetch the data. So while that fetching is done, we'll have to stall the CPU. CPU cannot go ahead with its operation until the requested data are given to the CPU, right? So it takes a long time. The miss penalty is a large number compared to hit latency. So because DRAM is a slow device compared to SRAM. So we'll have to stall the CPU for a significant amount of time. So in order for our concept to work, right, this large and fast illusion to work, we need to be able to say that most of the accesses, around 99.9% of the accesses, are hits at the highest level, hits at the SRAM level. So 99.9% of the accesses are served under 1 nanosecond. Only 0.1% of the accesses are served from the memory, right? So we need to make sure some really high hit rate like that. We need to make sure the hit rate at the top level is high, very high, not just high, very, very high, in order to reasonably support our pipeline concept, right? To get the, not just pipeline concept, to match the speed of the CPU. If our CPU runs at a certain clock rate, then we need to provide the data within one clock cycle for a memory request. Then very big amount of the memory request should be served at the SRAM level itself. Only very rarely, occasionally, we would have to go to the memory, right? So if it is like that, if we can ensure that is the case, then our CPU will work fine 99.9% of the time. But for that rare 0.1% of the time, the CPU will have to stall. We can't do anything about it, right? So but we can have this illusion of having a large memory at a very fast access time. So in order to maintain that, we need to make sure we get a lot of hits, very high hit rate at the SRAM level. Is that clear? Is the concept clear? right? So it's like when you're listening to music, you need to make sure that all of the songs that you would probably like to listen are available in the phone itself, because we don't really want to go to the computer and copy songs all the time, right? It takes a lot of time. So we would only like to occasionally copy songs from our computer to the phone. So we would like to listen to the music that we want to listen to on the phone itself nearly all the time, right? So the concepts are similar. So, right. Now, in order to ensure that this is the case, that we get a lot of hits at the highest levels, we use something called principles of locality. So even though we say principles of locality, these are certain characteristics that you find in computer programs by their nature, right? By the way we write programs, by the way how programs are compiled and assembled, by the way how instruction sets are built, right? By the nature of computer programs, they access only a small portion of the entire address space at a given time, right? So address space, imagine as the entire DRAM or the entire main memory, right? The entire space of addresses starting from address 0 to address whatever at the end of the memory, right? So those are the addresses that CPU can generate, the range of address space. So while a program can use all those addresses at different points in time, and at any given time it only uses a very small subset, right? If you take a very small window of operation in a program, the program will use only a small portion of the data that it will use in its entire lifetime, entire run, the overall run. In any small time window, it will only use a small fraction of data, right? And that is true. We know that because we are writing we know how to write programs. We know that is the case, and we know how assembly works. We know how ISAs, we know what ISAs are and all that. So we can understand that programs access only a small portion of their entire memory space at any given time, right? So based on that, we can define two principles of locality. The first one is called temporal locality. Temporal locality says recently accessed data are likely to be accessed again soon. Is that right? So if you think about programs which mostly uses things like if conditions and loops a lot of the time, right? Loops or recursive concepts, things like that, right? A lot of repetitive work are done in programs because programs are written to automate computations. So there are a lot of repetitive work, and in loops like this, you use a small amount of data, a subset of data repetitively for a number of times, right? So for example, a loop index will be used for the entire duration of the loop. Data used in a loop are very likely to be used more than once in the same scenario, right? Read again and write again or something like that. So one characteristic feature that you will see in programs if you analyze a program is that recently accessed data are likely to be accessed again soon. If you access a particular memory address right now, it is very likely, there's a high probability that you will be accessing that same address again very soon, right? After a few clock cycles, you would like, where you are very likely to access that same address. And this is a property that holds true for nearly all programs, right? So to a degree is different from program to program, but in all programs, you can see that recently accessed data are likely to be accessed again soon. That property is called temporal locality. That is locality of data in time. If you arrange the data that are accessed by a program in time chronologically, you can note that in time, the same piece of data are accessed quite close by. So that is the first principle of locality. Second principle of locality is spatial. Spatial locality says data located close to recently accessed data are likely to be accessed again soon. So that says if a piece of data at address A is accessed right now, it is very likely that you will be accessing address A plus 1, A plus 2 and so on very recently in soon, right? Very soon. Very soon, you are likely to access the next piece of data and the next one and so on. So if you again look at the loop operation, this is the other property that you can find about accessing data, right? Arrays, if you take an array in accessed in a loop, it is very likely that if you access the first element in the array, very likely that you will access the second one soon, third one soon after that, and so on, right? So that idea is known as spatial locality. Data located close to recently accessed data are likely to be accessed soon, right? So let's try to put this in line with our music example. So temporal locality. If you listen to a song, are you not likely to listen to that song again very soon? Right? It happens with most people who listen to music. If you listen to a song, you want to listen to it again soon, right after that even, right? So sometimes you listen to the same song 10 times before you do something else. So some very similar concept is available in programs when they're accessing data. And spatial locality is something like if you listen to a song by a particular artist, you are quite likely to listen to another song by the same artist next, right? Some related piece of data. If you listen to a song in a particular album, you're likely to listen to the next song in that album or another song in that album. So we have some similarity between the two examples, temporal locality and spatial locality. Locality in time, locality in space, right? So, right, we need to make sure that these concepts are clear before moving on. Is anyone having any issues or trouble understanding this? Please ask if you have a question, because we need to be very thorough with these concepts before moving on. Because now remember, we said that we need to guarantee nearly all the accesses are served at the highest level, top level of the memory hierarchy. And these are the two underlying concepts that supports this memory hierarchy to work as we want it to work, right? Only a small portion of data for a program is used at a given time. And in that, when trying to find what is that small portion at any given time, you can come up with two relationships. One is a piece of data that is used now is very likely to be used again very soon, right? And a piece of data that is used now, there's a high likelihood that the next or very closely located, physically closely located data are going to be used very soon, right? So based on these principles, we can decide what sort of data to keep in the SRAM. What is the subset of data from memory that you're going to keep in the cache or the SRAM device, right? So deciding that subset is done based on these principles of locality. Let's see how that is done, right? So that is done by the cache memory, right? The cache memory is, okay, it's a memory device. It's a memory used as a used at the top level in the memory hierarchy. It is the it's based on the two principles of locality that we just discussed. All right. So what data we are going to keep in the cache memory is decided based on those two principles of locality. So the two principles are very important. Everything will be based on that. Right. Okay. So temporal locality, it comes into the picture when we need to decide what to throw out from the memory, right? Not just what to keep in the memory, but what to throw out as well, right? It's like the two sides of the same coin. So evicting is what is being thrown. Evicting is throwing out a piece of data. So a cache controller, just like the controller in the CPU, there's a controller in the cache memory as well, right? So that controller needs to decide if there is a miss, if you need to go to the memory and fetch some data, then where are you going to keep that data? Based on that, you will need to throw something out of the cache memory, throw some existing data from the cache out. So that eviction is, it should be decided carefully based on temporal locality, right? So ideally, what would you like to do based on temporal locality? What sort of a data that you would like to throw out from the cache based on temporal locality, ideally? Can someone suggest an answer? Rarely used things. Yes, rarely used things. Exactly. So if we have 10 pieces of data in the cache, and we need to throw one out, we would ideally like to throw out the piece of data that was least recently used, right? Least recently used. We want to keep the data that are more recently used. The data that was not the most recently used are the ones that are that should be thrown out, right? So the least recently used data is ideally the one that we would like to throw out of the cache, right? So that is based on temporal locality. And spatial locality, how that comes into the picture is by handling blocks of data instead of words of data. Now, the CPU that we know, it refers to memory in words, right? You ask for a word from memory, you ask for ask to read or write to and from a word, memory word. But between cache and memory, right? Only between cache and memory, hidden from the CPU, we handle data as blocks of data, right? So this is similar to, say, when you're copying a song from your computer to your phone, you're copying a song because you want to listen to it, right? So instead of just copying that song, you copy the entire album, right? A set of songs from the same artist at the same time, right? You copy that entire bunch into your phone, because it's likely that if you want to listen to this particular song right now, it's likely that you would like to listen to another song from the same album, right? So because of that spatial locality, we handle blocks of data instead of words of data. Blocks are larger quantities. Several words go into a block. So we handle blocks of data instead of just bringing one word of data from the memory. We bring a block of data located at at consecutive addresses, right? If you wanted to fetch right. So yeah, so that is how temporal locality and spatial locality is taken into the implementation of a cache, right? So when deciding what to evict from the cache and handling blocks of data between memory and cache, right? So even though the CPU only requests individual words, cache handles blocks of data, moves blocks of data between memory and itself. So, right, so keeping that in mind, we can define the average access time for a cache, right? On average, the time it takes to access a cache is, for all accesses, for any access, you will take the hit latency, HL, right? HL is hit latency. So for all accesses, you are going to take the hit latency to decide whether this address is available in the cache itself or not, right? So that latency is going to be consumed for all accesses. Then, if it is a hit, we can assume that the time taken is only that. We don't have to spend any other time, right? There might be some small delays in trying to put the data into the bus, that kind of thing, but we can ignore them. The dominant component is the hit latency. Now, if the access was a miss, right? For the portion of accesses that are misses, you need to apply the miss penalty as well, getting the data from the memory, right? So for all accesses, you are going to spend the hit latency. Only for the portion of accesses that are miss, or only for the miss rate, you can apply the miss penalty. So based on that, you can come up with this average access time for a cache. Right. So what affects these different times then? The architecture of the cache itself, the design of the cache, the size, arrangement of how data is stored, the controller, how the logic of the controller, all that affects the hit latency, that is deciding whether the access was a hit or not, and also the hit rate. Hit rate is affected by the architecture of the cache. That is, if your cache is larger, then you probably can hold a lot of data in the cache, and then the hit rate is likely to go high. So yeah, so the architecture of the cache affects the hit latency as well as the hit rate. Then the architecture of the main memory, right? The DRAM memory, it decides the miss penalty. Mostly the architecture of the main memory, it affects the miss penalty. The time spent on communication is also there, the buses, that's also there, but the major component is the architecture of the main memory, right? So that's what decides the miss penalty. So then what remains is the program itself, right? The program and the CPU and the instruction set architecture. All those things decide the pattern of memory accesses. how and when loads and stores are done in your program. That is decided by the program, the algorithm, as well as the instruction set architecture and the CPU compiler and all those things, right? So those things affects the hit rate as well as the cache architecture. Okay, right. So we'll talk more about this when we talk about performance, but let's try to understand how a cache works, right? So that is the major thing that we'll be discussing under this topic. Right, so now how do we usually find data in memory? When we want to access memory to find a piece of data, how do we usually do it? We use an address, right? The CPU, it provides an address and either ask the memory to read from there or ask the memory to write the given data into that address, right? So we access the memory by using address. We understand the memory as a sequence of slots where each slot has an address, consecutive addresses, right? So a range of addresses like that, that is our address space, and we only provide an address from that address space and ask the memory to read or write there, right? So each byte size location in memory has an address, and we know that as the byte address. So let's look at this diagram and assume that this is our memory, right? So with the top slot, the address is 0. Addressing starts there 0. Usually, remember we refer to the memory the other way around, but here I've done it a bit different. So that is the address 0, 1, 2, 3, 4, and so on, and the memory continues down. You only look at the first few memory slots there, right? So each of these byte-sized locations in memory has an address, and we refer to that as the byte address, right? So if we take a 32-bit address, if we use a 32-bit address to refer to the memory, that means we can access 2 to the power 32 individual memory slots, individual bytes in the memory, right? 2 to the power 32. Now, if you take an example address like that, 0, 0, 0, a lot of zeros followed by 1, 0, 1, 0. So this is 8 plus 2, 10. So this is address 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Address 10, right? So this address refers to this byte in the memory, this slot, byte size slot in the memory. So this is a byte address. It refers to a byte. We understand that this refers to a byte, right? The CPU is built to make that built in that understanding, and the memory also supports it. Okay, so that is a byte address. Then we use the concept of words in CPU. We deal with words of data rather than bytes of data most of the time, and we align usually 4 byte size 4 bytes into a word. It might be different in different implementations, but usually the most common one is 4 bytes in a word, right? So the first 4 bytes we refer as one word, the next 4 bytes one word, the next 4 bytes one word. So here, if we take an address like this, we refer to that as a word address, right? So the last 2 bits here, the 2 least significant bits in the word address, you can use to refer to the individual bytes there. If you put a 1 here, then you are referring to the second byte. If you put a 0 there, you are referring to the first byte, right? Likewise, third byte and fourth byte you can refer to by putting 0, 0, 0, 0, 1, 1, 0, and 1, 1 here in these 2 least significant bits. So if we ignore those 2 least significant bits because our word size is 4 bytes, the rest of the address can refer to the word. The rest of this address can refer to the word. So this byte address refers to a byte in this word, right? So usually word addresses end with 00, right? If we know that this is a word address, it is usually 00. It doesn't mean that any address ending with 00 is a word address, but a word address ends with a 00. That is the starting byte of the word, right? So only this portion of the address is used to find the word in the memory. So that is the zeroth word, right? If you have a 0 here, it's the top word we have here. The next word has the next address, 0, 1. We are talking about the third word in the memory, right? 1, 0. So, right. I hope that concept is clear, right? Not all addresses ending with 00 are word addresses, but a word address ends with 00 because our word size here is 4 bytes, right? So it's a word address is always a multiple of 4. You should be able to divide the word by 4 without remainder, right? Okay. So this concept we discussed earlier also. I hope it is clear. So our CPU is built with 4-byte word size. CPUs in general usually deal with words rather than bytes of data. There are specific instructions like load byte in MIPS, which can load a byte, but that is from the programmers and ISA perspective. The memory side of it is implemented usually handling 4-byte words or whatever predefined size words, right? It can be 2-byte word or 8-byte word, usually 4-byte words, right? Right. So the other type of addressing that we will do is block addresses. Now, since we are going to deal with blocks between cache and memory, we have block addresses in addition to the byte and word addresses, right? So let's assume that we have 8 bytes in a block. That is, one block has 8 bytes, or in other words, 2 data words, or 8 bytes, right? So here, this is one block of data. That is a separate block of data, right? So first block, second block, and then here, because we have 8 bytes in a block, our addresses for blocks needs to only deal with multiples of 8, right? Multiples of 8. So we can ignore the 3 least significant bits and take only that. And only that portion of the address we refer to as the block address, right? This might be the given one here is actually a byte address, right? We know that this is a byte address because our system we are assuming 4 bytes in a word and we don't have a multiple of 4 in this address. So this is a byte address. And if we ignore the 3 least significant bits, the remaining portion of the address is referred to as the block address. Note the difference. In the word address, you actually use all 32 bits. You refer to the entire 32-bit address as a word address. Block address is a term you use to refer to the portion of the address that you need to identify the block, right? So all the bytes within this block have the same block address. Only this blue part is different for individual byte addresses, right? So that blue part is referred to as the block offset or just the offset, right? So that is to find either the word inside the block or a byte inside the block. you need that offset. If you want to find a given byte inside the block, then you need to use all these 3 blue bits. Then we refer to that as the byte offset. Finding a particular byte inside the block is done by this byte offset. But if you want to find a block, find a word inside the block, find one word inside a block, then you only need this most significant bit on the offset, only that, right? In our example, because we have 2 words in a block, we need this most significant bit to find that word. If this is 0, we are referring to that word. If this is 1, if this was 1, we are referring to the other word in the block, right? So that most significant bit in this example is then referred to as the word offset, right? So offset can be seen as 2 different ways. If you take all the bits in the offset, it's a byte offset referring to a byte within the block. If you only take a portion, more significant portion of the offset based on your block size, right, and word size, based on your block size and word size, then that portion we refer to as a word offset, which is used to identify a word within a block. Do you have any concerns, questions, or confusions about this different addressing? Any issues? No? Okay, very good. Right, so now the problem is we have all these addresses in the memory, all these bytes we are trying to access separately from the memory. We can access as bytes or as words or as blocks, but the cache is a lot smaller than memory. Right? We saw memory gigabytes, cache kilobytes or megabytes, right? As only a small fraction of data can be put into the cache. So how does the addressing work there? Do you see the problem? If we didn't have the cache, if we directly access memory like we assumed when we were discussing the data path and control, all we had to do was come up with the address from your address space, any address from your address space, a word address. You can give that word address to the memory and memory will give you the word, the data from there, right? Now, since we can't have all those addresses in the cache is on a small size, how can we access this data? If you only had the memory, if you say address 10, then memory knows exactly what address 10 is, right? You don't have to go and find that. You don't have to go and search that here. Address 10 will directly take you to the correct place in the memory. Just like when you're accessing an array in your programs, right? When you say index 10, you don't have to sequentially go and find it. Index 10 can be directly accessed, right? Because you have the memory address for that. So just like that. But in cache now, we only have a subset of data from the memory. How does the addressing work? If the CPU wanted to access address 10, can you just go and directly access a slot in the cache just like you access in the memory? Can you do that? Do you see the problem? How do you index the cache? That is the issue, right? So can someone come up with a solution? How do you, how can you find a piece of data in the cache? Finding a piece of data in the memory is straightforward. You have the address, you directly access that place and get the data. How can you do that in the cache? Can someone suggest a solution for this? Because the cache is smaller, cache, if the memory has a million addresses, cache can have, let's say, 10 slots or 8 slots rather. So can you go and directly access just like you access the memory? If you wanted to access address 10 in the memory, fine. In the memory, it's okay. In the cache, if you have only 8 slots, how does the addressing work here? Can someone suggest a solution for this problem? Any idea how to know that you're accessing the correct thing, you're reading the correct data? Very good. Caches store memory addresses too. That is the initial concept that we can think about, right? So yeah, can we store memory addresses along with data? That is what we have to think about, right? That is the way that we might be able to solve this. Can store address along with data, right? So in the cache, when we store a piece of data from a particular memory location, we can store the address of that piece of data as well. But that takes a lot of space, some extra space, right? And then the other problem is we would probably need to search when we want to make an access, right? If take that example, we have 8 slots in the cache, right? We are looking for the memory address 10, and if the memory address, the data from the memory address 10 is stored in the cache, we would have stored data as well as the address. Now we'll have to search through all these 8 slots to find whether the address is matching to the one that we want, right? So we'll probably need to do some sort of a search. It takes time. To do the search, right? So two problems come into our into this. It takes space to store the addresses. It takes time to search through these addresses, right? We can't directly access each of the 8 slot may be storing God knows what address, right? So we need to search. Now, in order to solve this, we need to have some sort of a mapping between the addresses from memory and addresses or slots in the cache locations, right? To have some sort of a potential mapping between all the addresses at the entire address space of the memory and the small number of slots available in the cache, some function, if you will, right? From memory addresses to cache locations. So the simplest mapping that we can have is called direct mapping. Oh yeah, we can do hashing as well, but we'll not go there right now because it'll complicate things a lot. So we can discuss that later. So the simplest possible mapping that you can do in when you're implementing a cache is called direct mapped cache. That is, if you take any address from the memory and try to map it to the cache locations, you only have one possible mapping, right? So let me quickly draw something here. So if you have a small cache, if you add a small cache here, right? Let's say four slots, a very small cache. Then if you take any given address from the memory, you can have only one location. So it's one arrow from here to there, right? So if you want to place that data in the cache, this is the only slot you can do it, right? Some mapping like that. So this is just a random drawing I did. So this is not the exact place this goes, but if you only have one place in the cache for any given memory address. If this address needs to go into the cache, you need to go to that one place, right? So that concept is called a direct mapped cache. Now right, this is how the address mapping is determined by in a direct map cache. You simply use a mod operation, right? Take the block address of memory. Now remember, we are only dealing with blocks between cache and memory, right? Blocks of data. So you take the block address portion of an address and apply the mod operation by the number of blocks in the cache. Simple, right? So number of slots in the cache actually. So if your cache can support only 8 blocks of data, that is 8. Then you mod the block address by 8 and the location in cache is given that. Well, the remainder will decide the location in the cache. So the location in the cache is, we usually use the term index for that, right? So if cache has 8 slots, the indices go from 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7, right? So the location is in the cache is referred to as the index, and that is determined by the number of blocks you can put in the cache, the size of the cache rather, right? So, and the number of blocks you can put in the cache is usually a power of 2. We built caches with slots in powers of 2. That is, you can have 1 block in the cache or 2 blocks. The cache can be 4 block size or 8 block size, and so on, right? So the number of blocks that you can put in a cache is usually a power of 2, right? Let's take an example. Assume our block size is 8 bytes, right? There are 8 bytes in one block of data, and cache can hold 8 blocks, right? So this is our cache, just like we discussed earlier, 8 slots, right? So our cache has 8 slots here. We have given 8 indices, 0, 1, 2, 3, 4, 5, 6, 7, right? So 8 blocks of data. So each of these slots can store 8 byte size block, right? Now take an example address. So this is a memory address, a byte address, or a word address. We don't care what it is. We only look at the block address portion of it. If you take the block address portion of this, ignore the offset. If you want to place this block of data in the cache, where will it go? It'll go there, right? So we take the block address, apply the mod operation by the size of the cache in blocks, right? We have 8 slots in the cache, and if we apply that, we will get the 3 least significant positions here, right? So this will be the remainder. If we divide this address by 8, the block address by 8, that's the remainder, the circle part here. The rest is divided without issues. So this remainder is the location in the cache, or in other words, the index of the cache entry. If you apply the mod operation and get the remainder, right? So this block if we bring this block from memory into the cache, it is mapped to there, mapped to this location. So if a memory request is being made with that block address, any word or byte within that with that block address, then you go to that index and get the block. So you don't have to go and search for the address, right? You don't have to store the entire address here with the data with this direct mapping scheme. That block can only be here. Because of that, you can directly access the cache using the index portion of this block address. Right? So this portion is referred to as the index portion of the block address. Now, when the CPU wants to access a piece of data or a word in this block, a word of data in this block, the index bit of the block address is used. So you know by the design of the cache, you know that you can only fit 8. So because of that, you take the 3 least significant bits of the block address and use that to index the cache, right? You can directly access the cache using that index, right? So that is how a direct mapped cache indexing works. Now, can you see a problem here? Can you see a problem with this concept? Now, yeah, we don't need to go and store the entire address along with the data now, because we can directly access the cache without needing to search. What is CPR sum address which has the same mod value? Exactly. Very good. Very good. That is, need another mapping to access things inside blocks. Need another mapping to access things inside block. That is okay. We can use the offset for that, Chamit. Yeah. The offset portion is there of the address. We haven't used that yet, but that offset is there to find things inside the block, right? Find words or bytes inside the block. So that is okay actually. But the problem is, as Buddhi said here, what if the CPU asks for some address which has the same mod value? Let's take an example. Now let's take this example here. Here, what is the mod value? 101 or 5, right? So we are still taking the block address. We are ignoring the offset for now. We'll use it later. Now here the mod value or the index is 101. So it should go there into that entry. Let's take another block address which has the same index portion. If you apply the mod 8 operation here, that also maps to the same location, right? So it's a different block address, but the index of it is the same as the previous address. So they both map to the same location. So as we sort of saw earlier, memory addresses, we have a lot. So eventually multiple addresses are mapped onto the same cache entry, same cache index. That is going to happen. So how do you solve this then? Now we can't avoid our storing the address here, but we don't have to store the entire address. We only store the remaining portion of the address, which we know as the tag. We refer to the remaining portion of the address as the tag, right? So we need to store the tag in order to differentiate between two block addresses which have the same index. So in the cache, when we build a cache, we need a data array as well as a tag array. So we need to append another section here to the cache. So we have to store the tag there as well with every data block, right? So now it seems like we are storing almost the entire address here, but that is because our index portion is small. We are only talking about a cache with 8 blocks, 8 slots, right? So that is a very small example. In reality, you have a lot more slots in a cache than that. So you will be using a significant portion of the address as the index, right? If you have, this is only for 8 blocks. If you have, say, 16, that many bits in the address goes into the index, 32, 64, and so on, right? So the larger the cache, you will use larger the number of blocks in the cache, your index portion becomes larger and tag portion becomes smaller. So you only have to store um, a portion of the address, like half or so of the address with the data block. But we can't avoid that. We have to have that because we need to check whether what is in the cache is actually what we are looking for, right? So we need to do a tag comparison when we do an access. But the good thing is we don't need to search the cache, the entire cache for that. We can directly access the index location using the index portion of the address and perform a tag comparison at that entry to verify whether what we have in the cache is what we want, right? So don't have to go and do a sequential search or some fancy search on the cache. Just have to do a tag comparison there, right? Okay. Right, so the structure of a direct map cache then looks something like this, right? So the index is actually not part of the cache. We don't store the index as a separate field in the cache. What you store is the gray part that we see here, right? The gray part. The first column we label as V, second column tag, and the third column data. So tag and data you have to store. Data is a block of data. Each entry will have all these 3 fields. Data is a block of data, several words. Tag is the tag portion of the address, which we need to compare whenever we access a cache entry. And V is called the valid bit to that we need to say determine whether this entry is valid or not, right? So for example, imagine at the very beginning of your program or the execution of your CPU, there'll be nothing in the cache. Everything will be in the memory. There'll be nothing in the cache. Cache is empty. So when you access, if you happen to have a tag match, you might read some garbage data, which is actually not valid data, right? So in order to denote that, we will use this V bit, valid bit. At the beginning, all the data will be marked as, all the slots will be marked as invalid. So we will not use garbage data by accident. But later on, you will see that the valid bit is used in other ways as well. We need the valid bit in other places as well. But the structure of the cache is that. So this light gray part is what actually is stored, right? You have a data array, a tag array, and an array of valid bits, just a one-dimensional thing, right? So index is what you use to access each of these entries. This is like the address of each of these entry, right? Okay, so we have about 10 more minutes. Let's see how a read access is made, right? So the CPU wants to read a particular piece of data from the memory, so it produces a word address, right? Let's assume CPU wants a word, not a byte, so it produces a word address, right? So the given address we interpret as 3 different segments. One is the tag segment, next index portion, and offset, right? So offset is what you use to find a word or a byte within the block, right? So this is the address that we get from the CPU. What else do we get from the CPU? If this is a read access, is this the only thing we get? If you recall the memory access stage of our data path, do we get any other information from the CPU? When we get an address along with that, do we get other information? Any other information CPU is giving the memory? Is it just the address? Do we have any control signals? Right, so if you remember, if you go and recall, we will have a read or write control signal to tell the memory that this access is a read or write, right? Or a load or a store access. Load instruction, store instruction. Differentiate between that, we have the control unit giving us this control signal, right? Us is memory now, right? Now, if we do, if we get an address like this and a read control signal, we know that the memory or the cache controller need to know that, understand that this is a read access. Okay, so this is a read access. That is the topic of the slide. So this is a read access. We know that by the control signal, and we get the address. We need to provide the correct data to the CPU based on this address. Okay. Now, from the address, because we know the structure of the cache, how many blocks we can store in the cache, we already know that. So because of that, we can directly index the cache. We can directly access the cache using the index portion of the address, right? So we don't have to go and look at this. This is not, the index is not stored on the combinational circuitry. Will direct you to the correct entry based on the index. So if the index was 101, we will be directed to that place directly, right? So just like in the register file. So index will direct you to the correct place, and we know that this is the cache entry. Then we need to verify that the tag of the incoming address that the CPU gave us is the same as the stored tag here. That is to verify that this block is indeed the block that CPU is referring to, right? Because there can be other blocks with the same index mapping to the same location. So we need to do a tag comparison. So what we will do is, once we locate the cache entry, we can take a set of wires from the tag array, from that index, from that entry, and compare that with the tag portion of the incoming address, right? So this is multi-bit signal. There'll be several bits here, wires here, right? From the tag, several bits, the same number of bits in the tag portion here of tag array of here in the entry in the cache. We take those two and do a compare. Okay, then we also need to verify that this is a valid entry as well. This is a valid entry as well. So we need to read the valid bit from the same entry, take the output of the comparator circuit here, right? So this is a comparator circuit which compare tag and incoming tag and stored tag. If they are same, you will get 1 here. If they are different, you will get 0 here, right? So if the valid bit is 1 and you get a tag match, you will get 1 here and then 1 here, and the outcome will be 1 of this AND gate. that means you have a hit, right? So you have a tag match and it's a valid entry. So you have a hit. So this is the place where we have determined that we have a hit. If you get a 0 here, we have a miss, right? So this process, doing this consumes that hit latency, right? So it usually has combinational delay of indexing the array, indexing the tag array, finding or getting to the correct entry in the cache. That has a combinational circuitry. So that is the combinational delay. The other part is the comparator circuitry we have here. Can you suggest what the comparator circuitry looks like? Just for example, assume that the tags are 4-bit size. You have 4 bits tag here. So 4-bit signal here, 4-bit signal here, right? Green one and black one. So what sort of circuitry can you use to do the comparison? Or rather, what sort of a gate you can use to do the comparison? It's actually very simple circuitry. If you try to recall the characteristic tables of the different basic gates that you learned, what can you use to build a comparator? What we want to do is to get a 1 if the corresponding bit positions, all corresponding bit positions are matching between these two signals, right? Can you think? XO. X, no, yes, that is correct. XO and not, yeah. You can use XO and not, or X no, right? Exclusive no. Yeah, very good, very good. Right, so you can build the comparator using a series of XNOR gates, right? So if you have 4 bits in the tag, you need 4 XNOR gates in parallel to compare the corresponding bits of the 2 incoming signals, right? So if you have 16 bits in the tag size is 16, then you need 16 XNOR gates. And then to aggregate the output of those XNOR gates into one signal using AND gates or multi-input AND gate, right? Okay, so right, very good. So that is the comparator circuitry here, and that is how you determine the hit. The time-consuming parts are the dominating parts are the combinational circuitry, which is used to index, right? Just from these bits get directed to the correct entry, that combinational circuitry. And this combinational circuitry, the comparator, and of course one AND gate here. Everything else is just wires, and wires will also have a delay, right, physically, but that is smaller compared to the combinational delays. So we can neglect that. So your hit time or hit latency is dominated by indexing and compare matching. Right. Okay, so now is the valid bit works like parity checking, Tushara. Not exactly, right? So valid bit is not auto computed. It is just to denote that the entry, that the given cache entry is valid or not. Like I said, at the very beginning, any entry is invalid because we didn't put any valid data there, right? Simply because of that reason. Later in the execution, there might be instances where entries become invalid. That means the data is not reliable to read. There may be something wrong with the data, right? So in that cases, we need to put a 0 in the corresponding valid bit position. So the CPU will not be given any invalid data, right? So that is the only idea. It's the role of the cache controller to decide when and what to write into a valid bit position, right? Entirely the cache controller decides that. So it's not automatically generated by based on data or tag. Valid is decided by the cache controller automatically, yes, because we designed the cache controller like that, but it's decided by the cache controller. Okay, now that is the tag matching and hit deciding part of our. Next, while this is happening, while the tag comparison and valid bit comparison, not actually valid bit extraction is happening, we can extract the data words given in the cache entry. Right? So while this is happening, while the tag comparison is happening, in parallel to that, we can extract or put the data block into a set of wires, right? So remember, the CPU is asking for a word of data, right? This is a word address, a word of data. So there'll be multiple words based on your block size. There'll be multiple words in an entry. We have to take the entire block into wires, set of wires here. Then how can we find the correct word out of this set of words we have here? How can we find the correct word from the block stored in the cache entry? Offset, yes, exactly. We need to use the offset, right? We need to use the offset. If this is a word address, the some least significant bits will be 0 because we are not interested in extracting individual bytes, but some more significant bits of the offset will determine how many based on how many words you have in a block. If you have 2 words in the block, then you only need to take the most significant single bit of the offset to select between these 2 words. So what is the circuitry? What is the logic element unit that we need for this? What is the logic circuit that we will need to use? MUX, yes. Yes, exactly. Very good. You need to use a MUX, a multiplexer here, to select the correct word out of the words available in the data block, right? So you need to use the appropriate bits of the offset and use that as the select signal for a multiplexer to get the correct word. Note that these are not single wires. These have multiple wires here, right? Each signal has multiple wires. So in the usual scenario, this will be a 32-bit word. That will be a 32-bit word. That will be a 32-bit word, right? So depends on your architecture, the size of the word, size of the block. All of these things change, right? So we can extract the data word and note clearly that extraction of the data word and the tag comparison can happen in parallel. Indexing the cache has to happen first, right? So that delay will be there. After that, tag comparison and the data word extraction can happen in parallel. You can do these 2 things in parallel without having to spend time, separate time, so that you can do them in parallel. So this is a combinational circuit. This is a combinational circuit. They'll have roughly similar delays, not exactly, but roughly similar delays. So you can overlap them. So then once you have the hit determined whether your access is a hit or not, you can treat the data word after that. If you have a hit, that means this is the word that the CPU was looking for. everything is good. So we can just send that word to the CPU, right? No problem. But what happens if this is a miss? If this is a miss, then the data word that we extracted it doesn't correspond to the address requested by the CPU, because we had a different tag, or we had an invalid entry. We might have had a matching tag but invalid entry. So, but most commonly we have usually we have a tag mismatch. So this is not the block that the CPU wanted. So we have a miss here. In that case, we can't send this data word to the CPU. Then we have to go and fetch the missing data block from the memory, right? So we'll talk about that in the next class. I'm hoping to have another class this Friday. I'll put up a notice in Fields about it. 1 hour class at 9. I'll put up a notice about it. So yeah, so we can stop here. If you have any questions, you can ask now. Or else, of course, you can ask in the discussion forum, so we can discuss there. Right. So from next class, in the next class, we will see the role of the cache controller when you have after you have determined the hit or miss, right? So these are basically combinational circuitry. We can implement it like that, and it will work every time. But based on the result you get here, 1 or 0, you will need to decide the next course of action. Sending the data word to the CPU on a hit, fine, easy. On a miss, what do you need to do? So that we will discuss in the next class then.